In video 3 of Module 7, we're going to continue our discussion of flows over immersed bodies, and we're now going to be focusing more on experimental external flows. And the reason why we have to discuss experimental flows is because the boundary layer theory that we've been studying for the first two videos in this module is actually very limited in its application. We can only apply it to flows that do not have flow separation. Okay, so if you remember your flow around a sphere had some flow separation once it passed the sphere. Okay, so it would have a flow separation that would occur at the top and bottom of the sphere, and here we would have a very, very complex pattern to analyze. Now, our boundary layer theory cannot take that into account. So what we can say is that the theory for boundary layers is very good for slender bodies and for very, very simple geometries. Now, in real life, we're not really interested in having systems that are all flat plates. Okay, we want to induce drag, we want to have more complex systems to be designed. And therefore, we have to reach out and use some experimental testing. And so a lot of what the researchers in fluid mechanics have done is used experimental testing extensively on specific external viscous flows to try and understand them and try and come up with rules and parameters that work for repeating experiments, for example, for wings or for airfoils of aircraft, for car design. Everything has been developed through experimentation. Now, lately, CFD has also, computational fluid dynamics, has also taken a bigger part in helping experimental testing be cheaper. Okay, if you can run 10 different configurations through a numerical method analysis, you can save some cost of creating 10 different prototypes. Okay, but the end all be all is still experimental testing to make sure that your design is correct. Okay, and we essentially have a problem with our mathematical theories is that we never get an exact solution. With experimental testing, you always get an exact solution. It is what you're getting is the truth and is what is happening in real life. So here below, I have a diagram of some of the terms that we're going to be using in this part of the chapter for experimental flows. And some of the terms that we can see that are very important are, for example, drag force. Okay, so the drag force is a force that is parallel to the stream. So drag force is parallel to the stream. Okay, and this is going to be a very important force that we've already talked about in our flat plate analysis, but that we're going to be able to talk about in our blunt body analysis and any type of body that we're interested in. Drag force is always something that we're interested in, no matter what we do. Okay, in a car, we want to reduce the drag force as much as possible. In an airplane wing, we want to reduce the drag force as much as possible. Now, in an airplane wing, we also have another force that's important, which is a lifting force. Okay, we need to see how much lift force a wing can do. We also have a side force, which would be, so if we have our velocity of our stream coming in like this, okay, so that's our velocity of our stream coming into our system, and we have this arbitrary body, the side force would be the force that is created sideways because of the body. So if wind is coming straight at you, you might have some side force if your body is not symmetrical. Okay, so if the body that it's hitting is not symmetrical, then there's going to be a side force to one side or another. And the secondary forces that we deal with are moments, and those are called the rolling moment, the yawing moment, and the pitching moment. Okay, this is just a way to explain what is happening in general. Okay, now if we look at a wing flow and a flow over a wing, if we have a wing shape like this, if we have a wing shaped like this, we can say that the lift force is up and the drag force is usually backwards. Okay, we have a force going back and our airflow is coming like this. So we have a certain lift force and a certain drag force, and we can see that our wind goes over like this and under here, and then rejoins at the back of our airfoil. Okay, and we can have separated flow or we can have not separated flow. It depends of how much of an angle you have. Okay, and we can also write that we can write the lift and drag in terms of coefficient of lift and coefficient of drag. Okay, which is a dimensionless form. So this is the dimensionless form of writing lift and drag essentially. Okay, which we've already visited a little bit, but we're gonna find an equation for CD and CL in this chapter where we can really use it extensively with a little bit of a different definition than usual. Okay, and we can say that in low speed flows, and what we mean by low speed flows is speed flows where we don't have compressible factors taking into account. So it's actually pretty high speed, but we're not looking at sonic flow or where we have compressibility happening. So usually our Mach in low speed flows is less than 0.3. Okay, we can say that CD is equal to a function of Reynolds number. Okay, and in general, CD is written in terms of characteristic area. So using our module 5 information, we can write an equation for CD that is a function of Reynolds, and we can rewrite it in terms of what we would actually get. So we have that CD is equal to the drag force. Okay, I'll put drag on the top, but this is just D, or the drag force, over 1/2 times rho times V squared times a characteristic area. And this characteristic area depends on our object. Okay, so our CD for a vehicle might be completely different from a CD for a wing, and we can't really compare a wing with a vehicle in terms of CD. We can compare them in terms of drag because that's an absolute value that we can see in real life, but we can't use a dimensionless parameter in order to describe it and compare them. Okay, but the nice thing with the CD is that we can compare cars of different sizes, or we can compare models that are half the size and use a CD to understand the coefficient of drag that we would have for a bigger car, for example. Okay, so this area or characteristic area can be 3 different areas. It can be the frontal area hitting the wind, okay, or the water or whatever it is. It can be the planform area, which is the area that we were calculating, for example, for the flat plate, which was B times H, for example, or it can be the wetted area. And I meant B times L for the planform area. Okay, so, or it can be the wetted area. And we'll go one by one to explain which one is which and which one is used for what. So the drag for a car, the coefficient for the drag for a car is found by the drag for the whole object, and we have the drag of the whole object over 1/2 times rho times V, which is characteristics of the fluid that the car is in. Okay, so if we take a car, for example, we would use the area of the car would be a frontal area. So it would be a frontal area, and this is usually the case for blunt bodies. So any body that is considered a blunt body, we're going to use the frontal area to find its CD. So CD is found using the frontal area. So if we have a car and we have a view of the car from the front with our wheels like this at the bottom, and let's say we have our windscreen in this sort of shape and the car continues, and then we have wing mirrors, for example, going out, and we have some, that's pretty much our area. Our frontal area is going to be whatever projection of the car we have from the front, from where the wind is coming. So it's this whole area, including the wing mirrors. Okay, so it's this whole area that is considered the frontal area. Okay, not just the area that first touches the wind. So the car front is what we're going to use for the area characteristic. And then we're going to be able to compare different models of cars with their CD based on their area and based on their drag. Okay, so it's going to be a very interesting tool that we can use. Now, for wings, for airplane wings and any wings used in research and in everyday life, we don't usually use the frontal area because the frontal area doesn't really affect our drag that much on a wing. Okay, it does affect our drag, but actually the size of the wing and the planform area makes a bigger difference. Okay, so usually for slender bodies, and the best example of a slender body is a wing or an airfoil, we can say that the area of the wing is going to be a planform area. And this planform area is going to be calculated as follows. It's going to be, so if we have a very simple wing like this, it's going to be the chord length, which is our length from the front to the back. So the length from here to here is going to be labeled C, okay? And it's a straight line from the front to the back, from the leading edge to the trailing edge. And it's going to be multiplied by the width of the wing. So if the wing has a certain width, like this, if the wing has a certain width, then you would just multiply by the width W. So our planform area is essentially the chord length, which is usually labeled by C or L, multiplied by the width of the wing. And that would give you your planform area. It's the planar area that you would have if you looked at the wing from the top, essentially. Okay, now for anything that's submerged in water, we usually use a wetted area. So for ships, for example, we use a wetted area, and it's usually the area of ship underwater. So it's the area of the ship underwater. Okay, and our coefficient of drag is a result of two different sub-coefficients. One of the coefficients of drag is due to pressure, due to added pressure. So this happens especially in blunt bodies or in bodies where we have some more frontal area. So this is led by pressure drag. And then the other type of drag is the drag due to friction, which we've already talked about in our flat plate bodies. Okay, most of the coefficient of drag comes from the friction in a flat plate. Okay, and I'm going to copy over a diagram now to show you the effect of the friction drag percent versus the pressure drag percentage as a body becomes more and more blunt, essentially. Okay, so we're going to look at the difference between blunt bodies and slender bodies. So I'm going to copy over a diagram here that will explain what is happening. Okay, so we have this diagram here, and we're going to focus on the first part of the diagram. And we see that we have on the top left, we have the y-axis says we have friction drag percent. So that's the amount of drag that is coming from friction. And on the bottom, we have a term called T over C. And T over C, as you can see in the description, is essentially the thickness over the chord or the chord length. Okay, so if we have a T over C of 1, we essentially have the following body. We have a length of the body equal to C, which is our chord length, okay, front to back, and the thickness of our body is also the same as C. So if we have a sphere, essentially, most of our drag is going to be from pressure drag. Now, if T over C is very close to 0, we see that 100% of our drag is from friction. So here we actually have the definition of what a flat plate would look like. The flat plate has a very long C and a very small thickness, okay? And sometimes even an infinitesimally small thickness, okay? It's just above our value of 0, because obviously it cannot be 0, if not, it would not exist. And anywhere in the middle, we actually have this type of shape where we essentially have a body that looks like a wing, and as we increase the thickness, it looks more and more and more like a cylinder, essentially. Okay, so we can see that it's described to us as a circular cylinder at the very top. So we have a circular cylinder at the top, and on the left side, we have a flat plate. Now, on this second graph, we're shown our CD versus the thickness ratio. So we can see that the CD at the very start for a flat plate is going to be very, very low. Now, we see that there's two different ways to measure CD. So CD can be either measured by planform area or by frontal area. And we're usually going to use planform area for the part here to the left, and we can even use it up to essentially here. And then we're going to use frontal area for more blunt bodies. Okay, so the more the body is blunt, the more we're going to use usually CD as the frontal area, based on the frontal area. Okay, so it's just two different ways of calculating this. Okay, so this would be the total drag versus the thickness when based on two different areas. Okay, so we can look at the effect of two different areas. Now we can see that the CD is very high for our T over C ratio that is very low, and it goes to infinity because our value goes to 0, so CD increases tremendously. That's not an accurate description of what's happening. Okay, it's not an accurate description of the actual drag. So what's important is to be able to correlate what the drag is doing versus what the shape actually is. Okay, so a little bit of a discussion here of that. Now, experimentalists throughout their time have also found that streamlining is very important. And I'm going to show you a diagram from your book that shows you the importance of streamlining a system. So if we have the following shapes, we're going to copy this over really quick. we can see that with different shapes, we can now experimentally find what is happening to those shapes if we just have them inside our flow, okay? And if we have velocity hitting essentially a rectangular cylinder, okay, just a rectangular piece of material, we see, okay, we just have a rectangle here on the top left, we can see that our CD is equal to 2.0. Now, if we just change the front shape to have this shape instead, we can now reduce our drag enormously by the fact that we have flow that is essentially staying stuck to the side. There's no backwash of flow and no flow increasing the pressure on our system. So the drag can already be reduced, the coefficient of drag can be reduced by half, by nearly half, just by rounding the nose. And in addition to that, if you round the nose and then you add an extra part to the back that is in a streamlined trailing edge, so a sharp trailing edge, where instead of having our flow leave our system and then create some backwash here, which creates some extra pressure to our system and extra drag, we can actually have our flow follow this line here and rejoin in the middle without creating much drag. Our flow stays connected all the time. And this CD actually goes down to 0.15. So we can now see how important it is when you're designing a vehicle, for example, or designing anything that's going to flow through air or water, how important it is to design it in a streamlined way. Okay, and this CD is equal to 0.15 would be equivalent to the same CD of a sphere that is much, much smaller. Okay, or a cylinder, sorry, a circular cylinder that is much, much smaller. Okay, so we can see that we have the same drag for a big, big object than something very, very small. Now, it's not the same drag, but it's the same coefficient of drag. Okay, so we have to remember that coefficient of drag is related to the area. So the coefficient of drag would be the same as a cylinder. Okay, so that's going to be very important and interesting as we move forward. Okay, some more interesting things in your book is that they give you some values for CD and for many different shapes that you can use as experimental testing, essentially. From experimental testing, they've been able to come up with a lot of different values for CD for standard shapes. And you can use these values as reference when you're either designing or when you're solving problems. So I'm going to copy over this diagram, which is table 7.2, and I'm going to copy table 7.3 as well in one go. So just give me a second while I copy everything. So essentially, from here, we can see that we have for a square cylinder, for example, for our shape, we have based on frontal area, we have 2.1. For a half cylinder, we have 1.2. And so we can find all these CDs that are dimensionless. And the important thing about a CD is that it's dimensionless. And the nice thing about dimensionless is that for any size, it's still going to be, the CD is still going to be the same. Okay, the CD is going to be the same for any size as long as the velocity is constant. Okay, so that's going to be very useful. Okay, we have some more information here with different shape sizes. Here we can see that we have a bunch of different shape sizes, and this is all coming from experimental testing and experimental repetition to be able to make these values possible for you to use. And then you just have to use them to solve your problems. And really, it's not about just solving problems, but it's actually about design, right? if you were to design a new shape that you say, okay, I'm going to use this shape for my car, instead of having to test the shape, if there's already an experimental test that has been done on that shape, then you're going to use that value. You don't need to redo the experiment and spend some extra money on it. Then in table 7.3, this is more for three-dimensional bodies. So it's looking at cubes or cups or short cylinders, as well as porous parabolic dishes, an average person, a bunch of different shapes that have been tested and have been compiled in this in this um, in this chapter. Okay, so there's a lot of information here that you can use for your information. Now we've talked about drag, and we know that our CD is equal to, if we go back to our drag equation, we have CD is equal to drag over half rho V squared times A. Now for lifting bodies, we're also interested in finding an equation for lift. And we're going to have the same relation between CL and lift as CD and drag. So we can write an equation for lifting bodies. So for bodies where lifting is an interest, we're going to have a CL that's equal to the lift, or L, over 1/2 rho V squared times A. And A is used in exactly the same way. So for lifting bodies now, we have two equations to use. We have CL and CD, which is drag over 1/2 rho V squared over A. And we know that CL and CD are, for lifting bodies, are a function of two different things. So we can say that CL comma CD are a function of Reynolds number, just like before for non-lifting bodies, just for straight bodies. But they're also going to be a function of angle of attack. Okay, so they're going to be a function of something new that's called angle of attack. And what the angle of attack is for a wing, for example, is the following. So I'm going to show you this diagram because I think this diagram is really useful in trying to understand what's happening. So in this case, we have a wing that is at a certain angle and is trying to create some lift force. Okay, we have this wing that's used to create some lift force. Now the angle of attack is the angle between this planar, this essentially horizontal line, and the line at which our wing is passing through, and this is our angle of attack. Okay, we're interested in the angle of attack. Now we can see that in our system, it seems like we have a very big angle of attack. If you look at an airplane wing, you would never really see it at this angle. I mean, you could actually see it at this angle, but it seems like the angle of attack is pretty high. Okay, but what's important to note is that the CL and the CD are a function of this angle of attack. So what that means is that we can draw a graph for lift versus alpha. Okay, so angle of attack is also written as alpha. And since it's a function of it, we can put our zero somewhere here because we know that we can have a negative angle of attack. So if the wing was in this position, we would actually have a negative angle of attack. And if we were to plot the lift of our wing, we would actually get the following graph. We would get a high lift, then a higher lift, and then we would have a drop off here. And this drop off is a drop off in lift when the angle of attack is so high that you get something called stall. And this something called stall is what we're actually seeing in this diagram. So if you look at this diagram, we see that we have our wing is in this position here, and we see that we have a wake that is being created, and we have no real flow here. So what we see is happening is we have a pressure 1 here and a pressure 2 here, and usually if our angle of attack is not too high, our pressure at 2 is higher than the pressure at 1. But because of this very big gap here, we actually have a pressure that starts to push in the drag direction only. And we get what is called our stall angle. So this is an example of when we have stall. And the reason we have stall is because our flow separates from the wing. If flow separates from the wing, we have very little speed here. We have very little velocity here. In this whole area, we have very little velocity. If we have very little velocity, it means the pressure increases. And that means that our wing is no longer lifting, essentially. Okay, so it's a pretty interesting concept. Now, I'm going to copy over one last diagram that we can comment on just to show you what this would actually look like plotted in the book as opposed to just by me on a small diagram. But essentially, we have that if we look at this diagram here with no flap, okay, a very simple diagram, we see that the lift as we go up in angle of attack goes up and up and up, and then eventually goes down. And we can see that the lift is a function of Reynolds number. So we can see that depending on Reynolds number, we have different curves. Same thing with the drag. With the drag, we have a low drag at 9 times 10 to the 6, a little bit of a higher drag at 6 times 10 to the 6, and we can see that our minimum drag is actually at an angle of attack of like 1 or 2 degrees. So experimentally, we've proven that our CL and CD, our coefficient of lift and our coefficient of drag, are a function of Reynolds number and a function of angle of attack. They're actually very sensitive to the angle of attack, even more than Reynolds number. Okay, so you're going to be able to use this in 2 study problems that are pretty simple. So we have 2 simple study problems on this experimental flow information. And this is really more of an introduction to experimental flows. It's not a fully developed explanation of how experimental flows happen, but you do the experimental flow, you do more of the experimental flow things in one of your labs. If you take the transport phenomena lab, you would do some experimental analysis of this type of thing using a wind tunnel, essentially. So this concludes Module 7, and next week in class, we're going to be going over Module 8, which will focus on Chapter 9 and will introduce compressible flow a little bit. So we'll see you next week in class.